Welcome to the deep dive. You know how incredibly captivating those virtual characters are when they move with really fluid, realistic agility? Almost like a parkour expert navigating a complex cityscape.
Oh, yeah, totally.
Well, today we're going to unpack how researchers are actually making those kinds of performances a reality.
And what's fascinating right off the bat is, well, the traditional way this has been done, motion capture. Think of actors in those specialized suits.
The ping pong balls.
Yeah, exactly. Meticulously recording every little nuance of movement.
Right. And okay, capturing someone maybe walking or running on a flat surface, that seems relatively straightforward.
Sure, that's doable.
But when you want that really breathtaking agility, like
Mhm.
picture someone leaping across a gap and landing perfectly on some narrow beam, especially in really varied, challenging environments,
Mm-hmm.
the complexity just skyrockets.
And the cost, too, right?
Oh, absolutely.
Yeah.
That kind of really detailed data is just incredibly hard and expensive to come by. So that data scarcity, it really puts a brake on how intricate and dynamic our virtual worlds can be, doesn't it?
It totally does. Existing methods, they often struggle, to create really convincing and physically believable movements when they don't have a direct, high-quality human example to draw from for that specific situation.
And that brings us right to the heart of our discussion today. We're taking a deep dive into a really groundbreaking approach called PARC.
PR.
Yeah, that's PARC, physics-based augmentation with reinforcement learning for character controllers. Bit of a mouthful.
It is, but the concept is key. It's from researchers at Simon Fraser University and NVIDIA, and PARC is tackling this exact challenge head-on.
If you think about the bigger picture here, PRC really represents a potentially transformative shift in how we create virtual agility.
Yeah, instead of being solely reliant on just capturing human performances, it uses this really smart synergy of machine learning and physics simulation.
To essentially teach characters how to move themselves.
Kind of, yeah. It's like they're learning the principles.
Okay, let's unpack this then. This sounds like a game changer. Our mission today is to understand precisely how PARC overcomes these limitations of traditional motion capture.
Right.
The core of it seems to be this iterative process, generating and refining motion data using machine learning, but guided by physics.
It's almost as if these virtual characters are learning the fundamental principles of movement themselves, through this loop.
This raises a key question then.
Mm-hmm.
How does this learning loop actually work? You said it's iterative.
Well, at its core, PRS employs two main components, and they continuously feed into each other. It's a cycle.
Right, so we're talking about a motion generator.
Mm-hmm.
That's the part coming up with the initial ideas for movement.
Yep. Generates the motion.
And then a physics-based motion tracker, which takes those ideas and makes sure they're physically possible and look natural in a simulation.
Exactly. It checks them against reality, so to speak.
Okay, we're definitely going to delve into how this dynamic duo works together to get this incredible agility.
So maybe let's start by really drilling down on this data scarcity problem. We touched on it, but getting high-quality mocap for agile terrain stuff.
Yeah, it's a monumental task. Absolutely.
Yeah.
I mean, imagine trying to capture the subtle weight shifts, the precise foot placements of a parkour athlete doing a flawless rollover, like uneven ground.
Or the split-second balance adjustments needed to land a jump on some really precarious ledge.
Right, the sheer complexity and just the endless variations in how they interact with different environments. It just makes it incredibly challenging to record accurately and consistently.
And that complexity, it directly translates into cost. You need to set up these really intricate capture environments, hire highly skilled performers who can actually do these demanding maneuvers flawlessly. And then you've got to process these massive amounts of data with meticulous detail. It all adds up very, very quickly.
Exactly. So while you might capture a decent run cycle on a level surface without too much trouble, capturing the nuanced changes in posture and foot contact as someone navigates, say, a rocky incline, that's a completely different ballgame.
Yeah, it really is. The data for those intricate, agile movements in complex terrain simply isn't readily available, not in the quantities you'd need.
And this is precisely the gap that PRC is designed to bridge. Its central idea, it hinges on this concept of iterative augmentation.
Iterative augmentation, okay.
So instead of needing this vast library of existing agile movements, it starts with something much more manageable, a foundation.
Okay, so how does this augmentation actually happen? What's the fundamental principle at work here?
Well, the core principle is to begin with a small, curated data set. They call them core skills.
Door skills.
Yeah, for moving across different kinds of terrain. Think like basic movements, walking, a simple jump, maybe a fundamental climbing motion, things like that.
So it's not trying to build everything from scratch. It has some initial building blocks. Got it.
Precisely. And then PRC expands this initial set of skills gradually, iteration by iteration.
Okay, and this is where the motion generator comes in.
Exactly. That's its job.
So tell us about this motion generator. What's its specific role in this process?
Right. So a motion generator's role is basically to create synthetic motion data.
Synthetic. So completely new movement sequences.
Yeah, essentially. Designed specifically for navigating new and varied terrains. It takes those foundational core skills and tries to figure out, how they could be adapted or combined in new situations.
Okay.
And it's important to note, this generator uses a diffusion model.
Ah, diffusion models. We hear a lot about those.
Yeah, they're a powerful type of generative AI. We've seen them do amazing things with images, audio.
And now motion. So it's learning the underlying patterns of movement from that initial data and then creatively generating variations for these new scenarios.
That's a very apt way to put it, yeah. However,
Yeah.
because it's generating these motions without direct immediate physical constraints,
Ah, okay.
the initial outputs can sometimes have imperfections, what the researchers call artifacts.
Artifacts. Like what specifically? What kind of issues might these generated motions have?
Things like the virtual character making unrealistic contact with the ground, maybe floating just a tiny bit above it.
Foot sliding, maybe?
Yeah, or even exhibiting sort of jerky, disconnected movements. These physically implausible motions, if you leave them unchecked, could actually mess up the whole learning process, degrade it.
Right, that makes sense. If the system keeps learning from movements that kind of defy the laws of physics.
It's just going to produce more unrealistic stuff down the line. Yeah.
So how does PRS address these imperfections then, these artifacts?
Okay, this is where the physics-based motion tracker steps in. It's the crucial second piece.
The tracker, got it.
Its job is to take these generated but potentially flawed motions and have the simulated character attempt to replicate them within a realistic physics environment.
Oh, okay. So it's like putting the generated movement idea through a rigorous physical trial.
Exactly. So the virtual character tries to perform the generated movement, and the physics engine determines if it's actually possible and if it looks natural, within the constraints of gravity, collisions, all that stuff.
Right. So during this imitation process, the physics engine just inherently imposes realistic constraints. The character can't simply float.
Nope.
It has to respond to gravity, interact correctly with the terrain. The motion tracker essentially refines the initially generated motion to make it physically plausible.
Okay, I can see the learning loop starting to take shape now.
Yeah.
So after the motion tracker corrects these artifacts, what happens to these improved motions?
Right. This is the key bit. These corrected, physically sound motions are then fed back into the data set.
Oh.
So this now expanded and improved data set is then used to retrain the motion generator in the next iteration.
So it's a continuous cycle of improvement. The generator creates, the tracker corrects based on physical reality. Yep. And the generator learns from those corrections to do even better next time.
Precisely. This joint training is absolutely vital. As the data set grows with more realistic and diverse movements, the motion generator gets better and better at producing plausible initial motions for new terrains.
And the tracker.
And the motion tracker becomes more adept at refining even more complex actions. It's a progressive enhancement of both components. They improve together in synergy.
That makes perfect sense. Wow. Okay, so let's delve deeper into the inner workings of this motion generator. What are some of the key technical details?
Okay, yeah. So as we said, it's a diffusion model. It's trained to generate sequences of motion, but these sequences aren't just created in isolation.
Right, they're conditioned.
Exactly. They're conditioned on several important pieces of information, a local height map of the terrain the character's interacting with.
So the ground right around it.
Yep, and a target direction, basically where the character is supposed to be going.
Okay, so it knows about the immediate ground and its overall goal. That seems pretty fundamental. What specific information does each frame of the motion sequence contain? Like what data is the generator actually juggling?
Each frame is quite detailed, actually. It includes the route, position, and rotation of the character, essentially, the location and orientation of its torso in 3D space.
Okay.
It also contains the rotations and positions of all the joints in the character's body.
Every joint. Wow.
Yeah. And also contact labels, which specify which parts of the body are touching the environment at that exact moment.
That is a significant amount of information to process for every single moment in the motion. And you mentioned it uses a transformer encoder architecture, similar to MBM.
That's right.
For listeners who might not be super familiar, what's the significance of choosing a transformer?
Well, transformer architectures are particularly good at processing sequential data, like motion over time, and understanding long-range dependencies within that sequence.
So it can see the whole picture of the movement.
Kind of, yeah. In this context, it lets the model consider the entire motion sequence and all the conditioning information, the terrain, the direction together to generate something coherent and natural looking. And MDM, the motion diffusion model, that already showed impressive results in synthesizing human movements from scratch. So it provided a strong foundation for PRs to build on, especially for these more agile actions.
Okay, and how does it actually incorporate the terrain and the target direction? What does that conditioning process look like sort of under the hood?
So the height map, which gives that detailed picture of the local terrain, that gets processed by a convolutional neural network, a CNN.
Right. CNNs are good with spatial data like images or height maps.
Exactly. The target direction, on the other hand, that's processed by a simpler multi-layer perceptron, an MLP. Optionally, the model can also look at the first couple of frames of a motion sequence as input.
Like a starting point.
Yeah, and those are also processed by an MLP. Then all of these processed inputs, the terrain features, the target direction, the initial motion frames, they get converted into what are called tokens.
Tokens. Kind of like how words are represented in natural language processing.
Yeah.
Is that the idea?
A somewhat similar idea, yeah. These tokens act like building blocks of information that are then fed into the transformer encoder. That lets the model understand the complex relationships between the terrain, the intended movement, and the resulting motion itself.
And how does it actually learn to generate these sequences? What does the training process involve? What's it optimizing for?
Right, so it's trained using a loss function, which is essentially just a way to measure how well the model is doing and guide its learning.
Okay.
This loss function has several key components. The main one is the reconstruction loss. That encourages the model to accurately predict the original clean motion from a version that's been artificially noised up that's part of the diffusion process.
Makes sense.
And this loss is carefully structured to handle positional and rotational data separately, and also the contact labels. Then there's also a velocity loss, which promotes smooth, natural changes in movement speed.
Avoids jerkiness.
Yeah. And a joint consistency loss. That makes sure the predicted positions of the character's body parts align with what you'd expect based on its joint angles. It uses a technique called forward kinematics for that.
Okay.
And crucially, there's a terrain penetration loss. That penalizes the character for, well, passing through the ground.
That terrain penetration loss sounds absolutely essential for keeping things physically real. You also mentioned some terrain-aware techniques earlier. What are those designed to do?
Exactly. So beyond that direct terrain penetration loss, they also employ this technique where during training, the generator sometimes has to create motions on completely randomized terrains.
Oh, interesting. Like surprise terrain.
Kind of. And in those cases, the terrain penetration loss is given extra weight, while the reconstruction loss is sort of downplayed temporarily. This forces the model to really prioritize avoiding collisions with the ground, even when it sees unexpected and varied terrain.
That's a clever way to build in robustness. And what about this blended denoising approach? That sounded particularly interesting.
Yeah, this is a technique designed to further refine how the generated motions interact with the terrain. So the researchers noticed that the generator might sometimes over-rely on the immediately preceding frames in the motion sequence, especially with a smaller initial data set.
Right. Might get stuck in a pattern.
Sort of, yeah. It could lead it to almost ignore the terrain sometimes. So during the denoising process, which is the core of how diffusion models generate data by gradually removing noise, they blend two predictions.
Okay.
One prediction is when the model considers both the terrain and the previous frames. The other prediction is when it only considers the terrain and the target direction. They blend these two together.
So it's like getting two slightly different ideas for the next bit of movement and then finding a middle ground between them.
Precisely. This creates a deliberate trade-off. Conditioning on previous frames helps keep the motion smooth and continuous, but it might come at the cost of less accurate terrain interaction. Only conditioning on the terrain ensures better ground contact, but might result in slightly less fluid movements.
So you need a balance.
Exactly. And the blending coefficient they found, it works well at 0.65 that determines the balance between these two factors.
Wow, that's a really nuanced and insightful approach to that problem. Okay. And how does the train generator manage to create these long, continuous motion sequences, the kind you need to actually navigate complex environments?
Right. So once it's trained, the generator can produce long sequences by auto-regressively conditioning on its own output.
Autoregressively, meaning it uses what it just generated to figure out the next step.
Exactly. It generates the next short segment of motion based on the previous segments that it has already created, along with the current terrain info and the overall target direction. It's like the character is constantly planning its next step based on where it is now and where it needs to go.
That sounds like it could potentially introduce some inconsistencies, maybe,
Sure.
or drift over longer sequences. Does that happen?
It could, yeah. So to mitigate potential issues like that, they use a batch generation strategy.
Real batch generation.
The generator creates multiple motion sequences, 64 in their experiments, all at the same time. Then they use a heuristic loss function to pick the best one from that batch.
So it generates options and picks the winner.
Pretty much. This heuristic looks at things like how much contact is the character making with the ground? Is it penetrating the terrain? Is it actually making progress towards the goal? And then finally, the selected motion goes through some further refinement using kinematic optimization techniques, just to smooth out any remaining jitter, reduce any lingering penetration issues, and make sure the contact with the environment is consistent.
Okay, that gives us a really comprehensive picture of how the motion generator works.
Wow.
Now let's shift focus to the other critical component, the physics-based motion tracker. How does that operate?
Right, the tracker. So the motion tracker is essentially a reinforcement learning-based controller.
Okay, RL.
Its core function is to learn how to control a physically simulated character so that it follows the kinematic motions from the generator very closely.
Reinforcement learning. So it's learning through trial and error within a simulated environment, like playing a game.
Exactly like that, yeah. They leverage the deep mimic framework, which has a really strong track record in training virtual characters to imitate a wide range of motions.
Yep.
And all the physics simulations are done using NVIDIA's Isaac Gym, which is specifically designed for efficient parallel simulation. Really speeds things up.
What kind of information does this learning agent actually have access to? What does it see or perceive about its environment and its own body?
The agent observes a very rich state space. It includes its proprioceptive state, things like the position and orientation of its torso, the angles and velocities of all its joints, whether different body parts are touching the ground.
Its internal sense of self, basically.
Kind of, yeah. And just like the motion generator, it also gets a local height map of the terrain around it. Crucially, it also gets information about future target poses from the reference motion that the generator produced.
So it sees where it's supposed to go next.
A few steps ahead, yeah. And to make the learning more efficient, all these observations are canonicalized to the character's local frame of reference. Meaning the data is transformed so the character understands it from its own point of view, regardless of where it is in the world or which way it's facing, makes learning more general.
Okay, so it has an awareness of its own body, the terrain right around it, and the immediate intentions of the motion generator. What actions can this agent take to control the character's movement then?
Right, the actions. The agent's actions are target orientations for proportional derivative controllers. PD controllers located at each joint.
PD controllers. Like tiny, precise motors.
That's a good analogy. They try to rotate each joint to a desired angle. The policy that the agent learns through RL determines what these target orientations should be at each moment.
Okay.
This policy is updated relatively frequently at 30 Hertz, while the underlying physics simulation runs much faster at 120 Hertz. So those PD controllers are like finely tuned mechanisms trying to make the virtual muscles hit the desired poses.
And how does the agent learn to actually follow the reference motion effectively? What's its goal? What's the reward?
Its goal is defined by a reward function, and this is inspired by that successful deep mimic approach we mentioned.
Okay.
This reward function has several parts that incentivize the simulated character to closely match the reference motion from the generator.
Like what?
Things like matching the position and velocity of the character's torso, matching the angles and velocities of its joints, aligning the positions of key body parts like hands and feet with the reference,
Mm-hmm.
and very importantly, matching the contact labels.
Ah, the contacts again.
Yes, ensuring the simulated character is making contact with the ground at the same times and with the same parts of its body as the reference motion. Getting those contacts right is absolutely crucial for achieving natural-looking, physically plausible movements.
That makes perfect sense. You can't fake good contact. And what specific reinforcement learning algorithm are they using to train this controller?
They use proximal policy optimization, or PPO.
PPO? Yeah, it's pretty standard.
Right, it's widely used and effective for continuous control tasks like this in RL. They also employ generalized advantage estimation, or GAE, which helps to stabilize and speed up the learning process.
Okay, so the tracker learns to imitate the generated motions within the constraints of physics. How does this lead to the physics-based motion correction you mentioned earlier? Where does the correction happen?
Right, so once the tracking controller has been trained in each iteration, it's then used to actually execute the kinematically generated motions within the Isaac Gym physics simulator.
Okay.
And by recording the resulting simulation, they get physically corrected versions of the original motions. The physics engine just naturally resolves any unrealistic aspects, like the character floating or passing through the ground.
So the tracker doesn't just identify what's wrong with the generated motion, it actually demonstrates a physically valid way to perform it.
Exactly. And sometimes, a generated motion might have issues early on that make it hard for the tracker to successfully follow the whole sequence.
Right, it might fail partway through.
Yeah. So to increase the chance of getting a successful recording, they use a clever trick. They initialize the character at different points along the generated motion.
Start it later in the sequence.
Yeah, and see if it can successfully reach the end from any of those starting points. The earliest successful attempt is then recorded as the physics-corrected motion data.
That's a really smart way to handle potentially flawed initial segments. Okay. So after all this iterative generation and correction, what kind of results did the researchers actually get? What are some of the most intriguing findings?
Well, the initial data set they used was surprisingly small, only about 14 minutes of motion captured data.
Just 14 minutes, that's tiny.
It really is, and it focused on fundamental parkour skills, vaulting, climbing, jumping, running, and these were performed on relatively simple terrains.
So a pretty limited starting point then.
Precisely. Now, they did do an initial round of data augmentation by randomly varying the terrains and using a basic physics-based tracking method. That gave them about 50 spatial variations for each initial clip.
Okay, beefed it up a bit.
Yeah. But the really significant advancements came with PARC's iterative process, after just 3 iterations running on a single high-end GPU for about a month.
Okay, so non-trivial compute time, but not years.
Right. PARC was able to generate entirely novel behaviors, things that weren't even present in the original dataset.
Whoa, really? Novel behaviors, that's significant.
It really is. Because it means we're not just limited to mimicking what we've seen before. The AI is learning the underlying physics and principles of movement to create entirely new, plausible actions. That's a fundamental shift from traditional animation or even heavily curated mocap libraries.
Wow, like what kind of completely new behaviors emerged? Can you give examples?
Things like seamlessly transitioning from a jump directly into a climb to grab onto a ledge.
Oh, cool.
Or executing a precise gap jump and then immediately catching a ledge on the other side.
Okay.
These were truly emergent skills, things the system figured out on its own.
That's incredible. It's not just cleverly replaying existing motions. The system is genuinely learning to combine and adapt fundamental movements in totally new ways. That really speaks to the power of this approach.
Exactly. And they also showed that by using the generator and tracker together, they could create very long-duration, coherent motions for traversing complex, manually designed terrains. It wasn't just limited to short, isolated actions.
And they back these impressive qualitative results up with quantitative data.
Right.
You mentioned some tables in their paper.
Yes, absolutely. Table 1 specifically looked at the performance of the motion generator across the PRC iterations. They measured key metrics like the final distance the character reached towards its goal,
Okay.
the amount of penetration into the terrain, the instances of unwanted contact with the terrain, and the frequency of jerky, unnatural-looking frames.
And the results.
Across all these measures, they saw significant and consistent improvements with each iteration of PR. Things got better each round.
And how did the performance compare to a motion generator that wasn't using this physics-based correction step? Did they test that?
They did, and that's a really crucial comparison. They trained a separate motion generator without the physics correction stage, and the results were quite striking. That generator produced significantly more jerky motions and many movements that were simply not physically plausible. It just didn't look right. This really underscored the vital role that the physics-based correction plays in ensuring the quality, the realism of the generated motions. And Figure 8 in their paper also gives compelling visual evidence. You can actually see how the generated motions become much more realistic and better at navigating complex terrain over the course of the PRAC iterations.
That visual confirmation must be very persuasive.
Yeah.
What about the motion tracker itself? How did its ability to follow the generated motions evolve through the iterations? Did it get better too?
Yes, Table 2 focused on the motion tracker's performance. It showed a clear trend of increasing success rates.
Meaning it could complete the motion more often.
Exactly. The percentage of times the simulated character could successfully complete the generated motions went up, and there was a decrease in the average error in tracking the joint angles as the iterations progressed.
So it got more accurate.
Right. It indicates that the tracker was also learning and becoming more accurate and robust in its ability to follow these increasingly complex and physically sound motions generated by the improved generator.
And you also mentioned a Table 3 that looked at the impact of that blended denoising technique.
Yep.
What were the key findings there?
Table 3 explored the impact of that blending coefficient, the Cia's value we talked about earlier. It effectively demonstrated the trade-off.
The trade-off between smoothness and terrain contact.
Exactly. Between achieving smoother motions indicated by a lower percentage of high jerk frames and ensuring better interaction with the terrain shown by lower penetration and unwanted contact. Their findings indicated that blending coefficient of 0.65 struck a good balance.
Oh, the sweet spot.
Yeah, leading to motions that were both relatively smooth and compliant with the terrain.
So it seems clear that this iterative co-optimization, this back and forth between the motion generator and the physics-based tracker, is a really powerful approach. What are the broader implications of this research? And what potential future directions do the researchers see?
Well, PARC's success really highlights the exciting potential here, the potential for training highly versatile physics-based controllers using only a limited amount of initial motion data.
Right.
This idea of co-optimizing the generation of motion with the physical tracking of that motion. It's a powerful strategy for overcoming those significant challenges posed by data scarcity in this field.
Absolutely. But the researchers, they're usually pretty honest about limitations too, right? What did they acknowledge still needs work?
Yes, they definitely point out that the generated behaviors might still occasionally exhibit some, unnatural-looking movements. It's not perfect yet.
Okay.
Also, while they use procedurally generated terrain for training, it still doesn't capture the full diversity and complexity of real-world environments.
Fair point.
And finally, the current version of the motion generator isn't quite fast enough for real-time planning.
So not quite ready for interactive games or robots that need immediate responses.
Not quite yet, no. That would be a crucial requirement for those applications.
So what avenues might they explore in future research then? What are some of the next steps they're thinking about?
Well, they suggest investigating better techniques for automatically identifying and filtering out any unnatural or physically implausible movements that might still sneak through.
Quality control.
Exactly. Incorporating more complex and realistic virtual environments for training is another key area for future work. Get closer to reality.
Makes sense.
And of course, significantly improving the speed of the motion generator to enable those real-time applications would be a major step forward. They also briefly mentioned developing a visualization and editing tool using Polyscope.
Oh, that sounds useful.
Yeah, it could be incredibly valuable for artists and researchers who want to work with and refine these generated motions, give them more control.
It certainly sounds like PARC represents a significant leap forward in making realistic, agile virtual characters more accessible and less reliant on all that expensive motion capture.
Indeed. By cleverly augmenting motion data through this integration of physics, simulation, and reinforcement learning, PARC offers a really promising path to significantly reduce our dependence on massive amounts of expensive human mocap data.
And that has the potential to revolutionize so many different fields, doesn't it? From creating more believable, more engaging video games and animated films
Definitely.
to significantly advancing the capabilities of robots operating in complex, dynamic environments.
Exactly. It really opens up a wealth of possibilities for creating sophisticated virtual agents and immersive experiences without the traditionally resource-intensive data acquisition processes.
This deep dive into Park has been truly eye-opening. It really makes you think, doesn't it? About how advancements like this could democratize the creation of sophisticated virtual agents and experiences.
Hmm.
I mean, what entirely new applications might emerge as these technologies continue to mature and become more widely accessible? Consider the profound implications of artificial intelligence, truly learning physical skills within these virtual worlds. It's a deeply thought-provoking prospect.
Absolutely. And for those of you listening who are eager to delve even deeper into the technical details,
Yeah.
the researchers have generously made their code and the associated data publicly available on GitHub, so you can explore the inner workings of PetWorks for yourselves.
Fantastic. Well, thanks for joining us for this fascinating deep dive. We look forward to exploring another cutting-edge topic with you next time.